And we'll just kind of see some more people trickle in. But the for this workshop, like this is kind of the time of year where the groups start to get like pretty small. So like um, feel free to like literally interrupt me at any time with anything. Um, this is entirely for y'all. So like we have like I just have like a vague plan of what I want to talk about, and so then this is just entirely for y'all. So if something doesn't make sense, or if you want me to slow down or speed up, like literally just like say something. Um, so just to kind of get uh, a feel for the room, how many of y'all are CS majors? Okay, sophomore, freshman, junior, freshman. Okay, so you haven't taken comp arc yet, or you're okay, yeah. Um, and then y'all are AET. Okay, cool. And you're AT, yeah.
I'm learning. I'm
Yeah.
learning.
Okay, cool. So this is a workshop basically about like memory. Um, this is more like technical than some of the other like workshops we've done. But the purpose of it is basically to sort of lay a good foundation for a lot of the more sort of complex aspects of game development. Things like building like big procedural worlds. So, for example, how does like Minecraft store so many chunks in memory? Um, like how can we make like infinite worlds, right? How can we have games like how does Vampire Survivors not like crash your computer, right? With so many like different enemies. Um, Basically, how do we handle lots of objects? How do we handle lots of information? How do we manage it in a way that's like efficient and a way that doesn't like crash your computer, right? So for a lot of those things, the engine does like heavy lifting for you, but um, really at some point it pays to understand sort of the fundamentals of what's going on. So how many of y'all like want to be like a game programmer, do some game programming? Yeah. At some point, you will encounter the the beast that is C++ plus plus if you haven't already, and there it will definitely pay to know about this stuff. We're gonna have a little like section at the end where we talk about like C sharp and other like similarly high level languages and how they deal with memory. Um, but other than that, I'm gonna like pull up my notes and we're just gonna get started, and we'll see kind of how much we can get through. All right. The first thing I'm gonna do is we're gonna be working mostly in C today. Who's written any C before? Congratulations! Today is your lucky day. We get to write some C. Um, so I'm literally gonna open Visual Studio. Uh, we're using Visual Studio because all of y'all have Unity installed presumably at some point. So like it's very easy to just open up a Visual Studio project, go to console application. If this is not there, this can very easily be edited. Yes.
On OBS, can you change the display to that?
Oh yes. Let me. Uh, there it is. Okay. So you quite literally go to console app, back, and then we'll just have it like make a program that prints hello world by default. We go next. Um, I already had this like folder set up. Actually, it might not be set up. Let me go. I think I had set it before and then deleted it. Documents. If I go to projects, and then make a new folder for it. Or actually, it'll probably just make it if it doesn't exist already. We'll see. If it blows up on me, it blows up on me. Okay. If you go to oh, okay, if you go to Visual Studio, what do you see when you make new projects? Oh, that's VS Code. You can also use VS Code. Yeah. Uh, in Visual Studio Code, you have to kind of configure things yourself. If you go, is CMake installed in the extension by any chance? In the meantime, we'll go ahead and make this and have it load. Workshop. Go create. And it didn't blow up on me yet. Notice how fast it made a project. uh, many years of using Unity has uh, made me expect like 10-minute load times. Um, Wait, but yeah, if you go to extensions in VS Code, let me just delete the comments. Can everyone else like make a C++ project? Not inside of a Unity project. If you just open Visual Studio itself, um, you should be able to go. Like literally what I did is I opened up Visual Studio. You should, like for example, if you have other Unity projects open, or if you have like any other like solutions open, you should see this. And then do you see create new? Yeah. And then you go here, and then you should have, if you don't have this, then you might have to go to the installer and get that, which I can very quickly look up how to do. Okay. Uh, Utu.
I downloaded the extension.
Okay. For CMake, if you go to the command palette, yes, that does help. Does that have, what does that include? Does that have a way to set up a project very quickly? If you go to the extensions, I don't think so. I think that's just for Java. If you go to the extensions marketplace, same place you got the C++ extension, and you search for CMake. And for the installer, if you go in here and if you go into wherever you search for apps and search for Visual Studio installer, you should see your list of, and then you can go and desktop development for C++ is what you want. Actually, I can go to y'all if y'all can't find it. Yeah. Desktop development. Yep. And then you can use VS Code if you want, or you can also just like install Visual Studio, whatever's easier. Oh, really? Oh, that's unfortunate. Yeah. Okay. Um, if you want to follow along, if you download the CMake extension, there's a CMake Quick Start. You can search up how to do that, and that'll also set up a project. Is just a slightly different way of doing it. Um, it's Windows really likes Visual Studio, so it just kind of ends up being the default. Like I think even if I also have done this before with VS Code, and it literally just generates solution files, which is pretty funny. But okay. But yeah, basically once you do that, what you'll end up with is basically a file that looks like this. And if we go and we just press run, you'll see it opens up a window and it has our output. Right? It has hello world, which is just what it's configured to run. We're all here? Good. Okay. Okay, so one very funny thing that Visual Studio does by default is it has these sort of they call like filters, right? Which are not actually the files on your computer. If you go up here and select show all files, this is what's actually on your computer, right? So we can see that it generated a debug folder because we're on a debug configuration by default. And then you can see that here's a bunch of like this is a .exe.recipe, which basically tells you where the path to your exe file is. And if I go and open my file explorer, I'll go to these projects. So this is where we created our project. You can see it in here, and then you can see x64, debug, and then here's the actual exe that we're running. So I can also go in here and sort of run that exe. It immediately exits, which is why you don't really see anything happen. But yeah, so then we have our C++ file here. We are not going to use C++ today. We're going to delete this. Or really, remove won't actually delete it, but I'm just going to remove it. Oh, actually, it does give me an option to delete it. Nice. Okay. And then we go to here. And then there should be an add. I'll go a new item. And I'm going to go main, and I'm going to change the file extension to C. So here is our C file. I'm going to go in here, and I'm going to make a main function. And I'm going to first include standard io.h. And I'm going to go printf. Hello. Printf. Hello world. /n. And then I'm just going to go ahead and return 0. Return 0 is convention for just return on success. So this is a very simple C program. And if I go in here and I build it, you can see we get the same like hello world output. Okay? So is everyone at this point still downloading? Okay. We're gonna like switch between like actually being in the code editor and then just talking, so like it can download in the background. But I just wanted to kind of show how to set this up from scratch. So this is a C file. Yay, we've all written a C program now. Okay, so the first item that we're going to talk about is kind of getting an understanding of what memory is. And as we kind of talk about this, we'll do some demonstrations up here so that y'all see and y'all can also follow along. So first of all, does anyone kind of have an idea of like what memory is? I know you have an idea of what memory is. Who else has an idea of what memory is? Okay. When you store stuff on your computer, right? Like what sorts of things do you store in there? You have like files, right? You have sort of all your apps, maybe you have like photos also, right? All of that is stored on something called like disk, right? Or like your hard drive, right? Your hard drive is kind of like your computer's like long-term storage, right? So like this is where all of your files live, right? Your disk can be like pretty huge, right? Like how much disk space do you all have? Like I know this has like a terabyte. So you're probably thinking of RAM, right? So you have 8 gigs of RAM, you said? So that's a lot smaller compared to like the average size of a disk, right? So like who else knows how much like disk space they have? 1.8 terabytes. I think if you go on Windows, if you can go like down here and have your C drive and
your SSD.
yeah, this PC. Yeah, so like here it tells me I have 179 gigs free out of 951. I don't know Max, unfortunately, but there's probably a similar way of doing it, right? So this is your disk space, right? So this is basically your computer's like long-term storage, right? But your disk is like quite slow, right? If you've ever like loaded a file or if you've ever like tried to save a file, that takes time to happen, right? So there's this other thing called memory, which is the information your computer stores like while it's actually running. So this is what you mentioned. You said you had like 8 gigabytes of RAM. I think this you can go and see if you on Windows you can go Task Manager, and so here's all the tasks you have, and then if you go to Performance and Memory, you can see that it tells you how much memory you're using for, and then how much memory you have. Why is this using 19 gigs of? Okay, Discord, fine. Sure. So you can see how much RAM you're actually using and how much RAM you actually have, right? I keep saying RAM. RAM stands for random access memory. Does anyone know what makes it random? Like, why do we call it random? There's actually nothing random about it. It just means that like I can go to anywhere in the memory, in memory, and find like what information I need, right? So, like pull up a whiteboard, right? So your computer stores information basically in sort of two primary ways. We have our disk space, which is long-term storage, and then we have our memory, which is the sort of information your computer has while it's running. If I close my computer and shut it down, memory goes away, basically. Like it's not going to stay around. This is things that are actually running. There are also things called registers, but we don't have to worry about that. This is at the CPU level, right? So the way that basically I want you all to think about memory for now is basically like a big block of data, right? So we're going to have a big block, and it's going to basically be like 32 gigabytes of space, right? Quick question: what is a byte? When I say byte, what does that mean? Yeah, basically. So we can't get the address of anything like smaller than a byte, right? Like what is actually a byte like numerically? Like what does that like represent? Yeah, so this is actually it's 8 zeros and ones. We say a byte is 8 bits, and 1 bit is just a 0 or a 1, right? So any sort of binary digit we call it a bit. 8 bits we have a byte, and then so on. We have kilobytes, megabytes, gigabytes, etc. Right? So all the information, right, on that you store in the program. So for example, like a floating point value, a character, or an integer, right? This has some binary representation, right? We're not going to get into the like how you actually get the binary representations of these, but unless y'all want to, we have a fair bit of time here. But basically, like whenever I open a Unity project and I type like float something, right? That has some binary representation, which at some point in time will be just stored here as a series of ones and zeros. Okay, everything making sense so far? So memory is just a big block of basically storage that our programs can use. Right? So everything is making sense so far? Okay. So let's go into our C file and let's make a variable. Okay. I'm going to go in here and include standard int .h, and then that's going to give me uint 32 t, and I'm going to say x is equal to, I don't know, 100. Okay, so the u stands for unsigned, right? So this is an unsigned 32-bit integer. Yes, so if I can also have an int 32t, which this can be negative, right? The other one can't be negative. This one is basically, the range of this is from 0 to, it's clear. The range of this is from 0 to the 32 minus 1, math? Yes, okay. This, on the other hand, because it has to account for negatives, it's like negative 2 to the 31 minus, I don't think, u minus 1 at the top, right? Something like that. So your range is slightly smaller. For reference, this is something like 2 billion, 2.1 billion, something like that. And then, so from like negative 2 billion to like positive 2 billion, right? So we have like finite space for, yeah. Once again, you don't have to know exactly how these are derived. This probably isn't correct, but basically we have some integer that takes up 32 bits of space. So that's how many bytes?
Um,
4, yeah. And then, so if I want a smaller integer, I can go uint16, I can go uint64. Is there a uint128? I don't think so, but
is this
standard is 32. So in a language like Java, for example, if I just type int, that is by default a just 32-bit signed integer. Um, in I don't know if C# has unsigned integers. It might do the Java thing and just only have signed integers. Um, Actually, I don't know, but this is also something that can be looked up. If you type long, for example, in Java or C#, this is 64-bit. You can also type byte in a lot of languages, and that just gives you what the equivalent of like a uint 8 would be, or actually in Java it would just be it has signed bytes as well. But this is all kind of making sense. We have different data types that all can kind of take up different amounts of space. Yeah. Okay. So when I go and I make this integer, and let's say I want to go and print it out, right? And then I go %d /n, and then I can give it the value I want to print out. So then I go and I run this, and you can see it literally just prints out 100. Okay. So when we make a variable like this, right, where exactly does this go in memory, right? So now we're going to talk about sort of like where do your variables go? Like when I make them, I know they have to be stored somewhere, but where are they going to be stored? So we're going to talk about something called the stack and the heap. Has anyone like heard these terms before? Yes, yeah. Who can kind of describe what the stack is?
it's well, the way we're learning right now is like calling methods, and it's kind of just like where you store all of your variables and the methods that you're calling. Once you finish calling the method, it's popped off the stack.
Yeah, exactly. Yeah, exactly. So that's one thing the stack is used for. You mentioned push and you mentioned pop, right? So what does that mean? Yeah, exactly. So you can think of a stack as like literally like think of it like a stack of cards, right? If I have something that I put onto the stack, I put it onto the top, right? And then I have another thing I want to put onto the stack, I go and I add it to the top. Okay? And then I can just keep adding things to the stack. This is called pushing onto the stack. Okay? If I want to remove something from a stack, I do something called popping, which means I go in here and then I can get rid of this, and then I can go and I can get rid of this, and I can go and get rid of this. So the convention for a stack is I can push something on top of the stack and I can remove something from the top of the stack. So like there's a very scary packet of discrete math worksheets here. I have a big stack. I can't just go like rummaging through the middle of the stack. I have to go and I have to take something out of it like this, and I have to go and add something on top of it. Does that kind of make sense? Okay. It's worth noting that your actual like hardware, right? Your actual RAM doesn't have any like concept of what a stack is, right? This is something that's entirely managed by the program. So when I like run a .exe file, for example, so I run a program, right? That program is going to go to the operating system and be like, I will initialize myself with some amount of stack space, right? And this is determined ahead of time. It's like I will have this much stack space. It's usually a very small amount, right? So let's say I have a program that gets loaded in. And so I have my program main.exe. And it's going to say, I'm going to take some stack space, right? And so this is the space that I'm going to reserve for my stack, right? So anytime I want to add to it, I'm going to push to this region of memory, I'm going to pop from this region of memory. What that looks like in practice is we have a pointer, right? It's literally just a number, right? And memory is a place where you can read and write something to, right? So I can go and I can move this pointer over, right? And in this space, I can write whatever data I want, right? So you can imagine that there's some stack pointer, which is describing some location in memory where my stack currently is, right? I have some stack pointer, and then after I have pushed something onto the stack, by convention, the stack usually grows downwards. So my stack pointer is now 4 bytes lower than it was. Is this kind of making sense? Okay. And then this is used for all sorts of things, right? By default, these sorts of local variables, they just go onto the stack, right? It's also used for things like you mentioned. Whenever I call a function, right, I need to basically save information about where I'm coming from, right? So for example, if I have main, and then I might have some function f, or I'll have some function add, which takes an int x and an int y, and then return x plus y. And I go in here and I say add, or so I'll say like uint 32 ty is equal to add 100 and 200, right? Basically, when I go here, right, I was in main, now I have to go all the way to add, and then I have to have some way to come back. So internally, there's some like state that has to be saved, right? So like, do you know what sorts of things get saved whenever you like call a function? Local variables. Sorry? Yes, the return address. So return address. So I need to know where to come back to, right? Also, there's a calling convention for, have you all talked about registers yet? Registers are basically like, they live in your CPU. They're basically like really short-term storage. So like a processor might have like 32 general purpose registers, and basically it'll pull data from the register into pull data from like memory into the register. So there'll be, whenever you start doing assembly, you'll have basically some kind of load function which loads at some kind of memory address. So you have some address here. And then you'll load this into a register, say like x1. And then x1 is a register that lives on your CPU, and then you can execute instructions like add x1 and some other register. Right? So this is like your like ultra short-term storage. It's the things that your CPU is actually working with, basically. We don't quite have to get as low level as that for the other things, but actually maybe we might. We might look at some assembly today, depending on how y'all feel about that. Okay, so you have to know where to come back to, right? So you go in here, you go add. Your program is going to basically go somewhere else, right? And ask where to come back. So all of that information is stored onto the stack, right? So you can imagine that, and kind of draw a picture here. Here is your stack pointer at the start of the execution of the program. I can go in here, and whenever x gets made, right, you push, you basically push the value like 100 onto the stack, right? So this is where that variable lives. When I say like an address into memory, does that kind of make sense? Sort of, yeah. So an address into memory is just a location in memory. So whenever, whenever I mentioned, for example, that I want you all to think of memory as just a big block of data, right? An address basically tells us where to look in this block. So I can have an address that points here. I can have an address that points here. I can have an address that points here. Okay? And then this basically just gives me a location memory, and I can read bytes from it, right? So does that kind of make sense? Okay. Too fast or too slow for now? Or kind of just good? Okay. So those are stack variables. Okay. Let me see if I had anything else I wanted to talk about. Okay, so we've talked about how things get added onto the stack. Now let's talk about how things get removed from the stack, right? So the nice thing about the stack is you can see these are very quick operations, right? You literally just take whatever the current stack pointer is, you subtract 4, and then that's the space where your like variable will go. This can be entirely determined at what we call compile time. So compile time is before your program even runs, right? You'll kind of know the concept of like compilation, more or less, yeah. So it basically, this is something that your compiler can determine exactly where this variable is going to go before the program even runs. It just knows it's going to be at stack pointer -4, right? And then stack pointer gets initialized by the operating system. So you don't know exactly, but you can say wherever stack pointer happens to be, right? Give me that -4, right? And it can just say that. This is really convenient because the stack is really quick, right? It doesn't have to do any complex operations. Saying u at 32 x is equal to 100 is just about the simplest form of initialization you can have. So when you think about the stack, I want you all to think about a small region of memory that's also very quick to access because it can be accessed. You know exactly where things are going to go ahead of time. Okay. So now that we know how things get onto the stack, we can talk about how things get off of the stack. Okay. So I think most of y'all, if you've used like a language like Java or C# with Unity, you kind of have an intuition of scope. So I'm going to give you a couple examples, and I want y'all to tell me sort of more or less what's going to happen. Right? Yes.
In a stack, hypothetically, are you only allowed to access like the most recent added thing? This one, can you access everything?
Yes. So it's not like a true stack in the sense of like your data structure stack. It's a stack in the sense of like kind of how we tend to use it. For example, you have like whenever you push something on a stack, you subtract 4, and then that's the space you can write, and that's like kind of like a stack. And we'll see here it's also similar when you pop from it. But literally all the stack is just a region in memory that we have sort of pre-allocated for us, and that stack pointer. And the stack pointer is just a number. So we can do with that number pretty much anything we want. Exactly. So there's also, have y'all talked about assembly at all in your classes? You'll see, so the stack pointer is an example of a register, and you'll see that. There's also a register called like the frame pointer, which is basically just a pointer directly into the stack. It's like a fast track. So you can do all sorts of crazy stack manipulations. So you're not tied down to the rule of, oh, I must push or oh, I must pop. You can have any offset from the stack that you want. And programs will frequently do that for optimization reasons. But yeah, not so important now, but if we wanted to talk about that. Okay, so I'm going to make an example here. I'm going to stick to using, I think we have the idea that that variables can be of a fixed size, so I'm just going to switch to using int. Funny enough, there's no guaranteed size of this. This can be pretty much up to your system how big it wants an int to be. This can be 32 bits. In all modern systems, it is 32 bits. But there's nothing stopping a compiler from saying, this is actually like 35 bits or whatever. Or, you can do crazy things. There are processors that have 24-bit integers, right? In modern languages, thank God we've standardized this, and this is always 32-bit. But funny example of why we tend to use sort of the fixed size integers, right? But for the sake of simplicity, I'll say that int x is 5. Then I'm going to go in here, I'm going to say if true. This works exactly as it might for, oh, right, we're in C. Okay, if 1. Uh, I could, can I import standard bool? Or sorry, not import, include. This is std standard bool.h. I can't type today. Std bool.h. C is the language where you have to import your booleans. Okay, so if true, then we'll say maybe like y is equal to, and then this will also be an integer. And we've all seen for loops here, right? So for int, let's say j equals 0 for funsies. J is less than 10, j plus plus. Do int z is equal to 50. Okay, so this is like mostly like relatively normal looking code, right? If you've written any other sort of language, right? Quick question, can I say y is equal to z plus 5 here? Why can I not say this? Yeah, exactly. So this z lives inside of these brackets, right? This is what we call a scope, right? So whenever you have brackets, what you're basically defining is a scope. So this is where like z lives, right? So internally what's happening, right? The stack pointer is at some point here, right? Here we're going to push z onto the stack. And remember what happens with the stack? We can pop from it, from the top. So the moment this bracket ends, right, we're going to pop z off of the stack.
I have a question.
Yes.
Since we're reinstantiating every time, is there like one time we run, does it make it and pop it off at the same time and then make a new one? Or is it just, yeah?
Well, the answer is it depends. The compiler can pretty much do whatever it wants. What you're saying of like constantly recreating it, it could do that. However, most compilers do optimizations. So like a compiler can see this, and actually if I was really to compile this, if I switch to release mode, which will turn on all of the optimizations, like this code probably won't even do anything. Like it'll just look at this and say, this is the most useless thing I've ever seen. I'm not even going to bother with this, right? So in practice, your compiler will optimize things to try and make things as performant as possible. So did you all understand kind of what the question was? She was asking like, every time I go through J, is it going to push to the stack, pop off the stack, push to the stack, off, pop off the stack? And nominally it seems that way, right? But in practice, your compilers are smart enough to kind of notice like, hey, I don't have to do that, right? I can be smarter about this, right? However, even if it does decide, oh, I'm just going to push it beforehand, right, or do some other crazy optimization, the language rules still apply, so I'm still not allowed to access Z. Does that answer your question? Uh,
I'm not saying we'll be able to access it, I'm asking about the pushing and popping.
oh, it really just depends on what the compiler decides to do. Yeah. You'll find that the compilers can pretty much do whatever they want. And actually, it's not uncommon for a compiler to basically look at a for loop and basically pre-compute the entire. It's not uncommon for. Hello? Okay. It's not uncommon for a compiler to basically look at an entire for loop and basically say, oh, I know what the answer is. So it really depends on what the rest of the code is. If you are really interested in the assembly, you can always on Windows, on Linux, you have just objdump built in, but you can always run, and we might do this later if this is something that interests y'all. On Windows, you can run llvm objdump. Hello. -d, and then you can go to some .obj file, right? So if you go into here, and you can see we have this obj file. We might look at this later. This will show you exactly what you're your processor is running. So if you're ever interested in what the compiler actually did, you can always look at that, right? So we all kind of have like an intuitive understanding of scope. So like the moment you get off of these brackets, you're not allowed to access Z anymore, right? Um, so that's another like really convenient part of the stack is you don't really have to manage your own memory. Sort of things are pushed onto the stack as they're created, and the moment you end a scope, it just pops off the stack, and then all the cleanup is handled for you. Okay, everything good so far? Okay, so that's the stack. The stack is small, it's convenient, it's quick, it's determined at compile time, is what we've looked at. I think if there's anything else I wanted to show y'all. Okay, so now let's look at something called the heap, right? There's something called the heap. So does anyone kind of has heard of this term before with memory? Yes, yeah. It gets kind of confusing because there's something called like the heap data structure, which is like a tree-like structure where you have like things in a sort of order. The heap has nothing to do with that sort of data structure you might have heard of. Your heap, you can think of it as in contrast to the stack in the sense that your heap is quite large, right? Your heap is also dynamic. It can grow and it can shrink. So basically what happens is when a program starts up, so if I do sum.exe, that your program is going to go to the operating system and it's going to be like, I am requesting this amount of heap space. And your operating system is like, okay, here's your heap space. And then so you'll get a region in memory that's quite a bit bigger, like significantly bigger than the stack, right? And this can grow and this can shrink. Your program might decide at any point, I want more heap space. Or it might decide to, the operating system might also decide to reclaim some heap space. So this is much more unstructured than the stack, right? So your heap is unstructured. It's also what we call dynamic. So before we mentioned that the stack everything was determined at compile time, right? With the heap, that's absolutely not the case. Everything has to be determined while the code is running. And so we'll look at some examples of that as well. And then so you can think of this, and this is managed, it's managed by the program itself, by the program. So your program is going to decide where I'm going to put something, where I'm not going to put something. Before it was your compiler. Your compiler was saying this variable will go at stack pointer -4, right? And that's where your variable will go. On the other hand, your heap is managed by basically the C standard library. It is literally a program, which we'll see in a second, that goes and decides where things go. Okay? So can you all kind of think of a reason why we might want to use a heap? Like, why is the stack like not enough for us? So the heap it's unstructured. It's much larger. It's determined at runtime. And it's like managed by the program. Yes, exactly. So, for example, if I have this integer, the compiler knows exactly how big this integer was, because remember we specified it. We literally wrote uint32t. Yeah, but the compiler doesn't always. We don't always know how big we want our variables to be. One easy example of this is if you've ever used a string. In C, they're going to be a little bit different, but bear with me here. Str is equal to, for example, hello world, right? In this case, it knows, right? But you can have a string that's of like different sizes, or maybe string is not the best example. When I have an array of something, right? And I'm deliberately not making an array just yet, just so that we can see it later. But if I have an array, right, of some amount of objects, right? In C sharp, you can quite literally go like int. You can go like int array, my array is equal to new int array. Of course, this is not like C, but and you can put any number that you want in here. You can have the user input a value, and and just make an array of size n, right? Can you see why there's no way for the compiler to know where this memory should go, because it doesn't know how much memory it needs, right? And by the way, y'all are familiar with kind of like what an array is internally. Like it's literally just a chunk of memory, right? So it is literally, an array is quite literally, here's my memory, give me a slice of it, right? It is a contiguous block of memory, right? Is internally what we're kind of looking at, right? So you can see if you don't know how big your array is, right? How do I know where to put this, right? How do I know how much space to put at compile time, right? So this is the reason why the stack by itself is not enough, right? Is because we have some variables, some data, where we have to decide dynamically how much we need, right? And this is the same with strings, right? We don't necessarily know how long a string might be, right? A string internally is just an array of characters, right? Does that kind of make sense? Why this is just an array of characters? Yeah. Okay. So this is kind of the motivation of why we need the heap, right? But we've also looked at that the heap has sort of things that we don't like, right? It's unstructured. It has to be managed by the program, right? So like, how do we do that, right? How do we actually access the heap, right? In its most basic form, we have something called malloc, right? Does anyone know what this stands for? Yes. It stands for memory, like allocate. It means I want some amount of memory that I want the program to allocate for me. Okay. So let's say I have my array, and I've decided I want an array of 100 elements, right? And you can imagine that there's some sort of complex set of computations that happens before this to like your compiler will see, oh, I know you want an array of 100. That's totally cool, right? But there might be some the function calls that we don't exactly know how many elements we'll want. Okay, so some unknown element, some unknown size, right? And I go in here and I'm like, well, okay, well, I need space to put this, right? So, and let's say I want an array of, we'll start with void pointer. Bear with me here. We'll look at what this makes sense. But I have some array, okay? And I want space for 100 elements, okay? So I'm going to go in here and I'm going to say, okay, give me space for 100 bytes or n bytes, right? So this is going to go in and it's going to call malloc and it's going to say, give me enough space for 100 bytes. If I want space for 100 integers, well, then I need size of int times n. So I want enough space for 100 integers. Does this kind of make sense? So you're basically going and you're asking the program very nicely, give me enough space for this amount of stuff. Where is this going to go? You don't know. You have absolutely no idea. There is a actually remarkably complicated set of algorithms that goes into determining where this gets placed. And you can imagine why this is the case, right? Actually, we'll talk about it once we think about like how do we actually get rid of this. But there's a ton of complexity that goes into what actually happens when you call malloc, right? But for now, I've made my array. I don't think I have to include anything with malloc. I think that standard IO should include malloc, yeah. And then I can index into this in the same way. And actually, so this is where we're going to have a void pointer. I promise we'll get to exactly what this means in a second, but for now, just bear with me. I'm going to cast this to an int array. And now I can use this as I would use an array in any other language like Java or C#. I can go and I can say, oh, my array of 0 is equal to 100. Oh, my array at 1 is equal to 200, etc. And I can go in here and I can go and I can say, I'm going to printf %d. I can say, oh, okay, give me the array at 1. And I can go and I can run this, and then we can see it didn't like that for some reason. Yeah, 1 equals 200. Is it giving an access violation? Oh, it is. It's been a while since I've written C. Wait, Bernice, do you know?
What?
Why this is
Oh, why it's not working?
we were gonna get to access violations in a second. Let me print the address of array. Oh, gosh. We'll do something else like that. We'll just print what array is.
Right? This is funny.
Is it not letting you write into it? Let me try.
And your costumes were right.
I believe so. Let me go into an online.
Oh, wait. Well, you don't have to do size of int thing, right? It's like the same as like the size of int.
Mm.
Like when you make, because you're making an array of essentially like int pointers and not like ints. Is I forgot how many bytes is an int pointer versus an int?
Pointers are 8
Is
bytes, I
it-
believe.
so- And isn't an int 4?
Yes.
So is it or no?
Maybe. We're about to see.
No, like size of int. Like don't you need the size of int pointer?
Very possibly. It should still have enough space, I believe. But
Yeah, because you only have
yeah.
the first two, but
Oh no, that still gives me the access violation.
yeah.
Let me go online and see if we import malloc. Do we include malloc? I think you quite literally need to include malloc. Oh, wait, that's hilarious.
Is the pointer still in?
Yeah, because it's a pointer to the start of the array, right? Why is that? Oh no, that works. Okay, so then that gives you 200. Standard I/O should include. Okay, funny include errors, but yeah, no. Okay, so the only problem was that I forgot to include. I forgot to include malloc, which is very funny. Okay, so we're back here. Whoopsies. Okay. And then we'll ignore the error because that's not doing anything. But okay, so we've basically requested some amount of memory from the operating system, right? And what this int pointer is, right? So remember how we had integers, right? Now we have a pointer to an integer. So we say that there's some like integer that lives in, there's some integer that lives somewhere in memory, and we want an address to it, right? So this is not the integer itself, it's some pointer that tells me where to go and find this. So I can actually go and I can print out array, and you can see it gives me this big number, right? This is where my array lives in memory, right? So this is a number that represents, oh, here's where I go to look for my integer, okay? So that this star means that this is a pointer to an int, okay? And then, so malloc by default will return what we call a void pointer, which is a pointer with no type. So if we want to specifically have sort of an array of integers, we would cast this to like an int pointer, okay? And then, so what this 0 index does is it goes in and it would go in and it would say, okay, give me the 0th element starting from that pointer, right? So this is exactly the same as going, basically, dereference array plus dereference array. So this will go to this address and then give me the value from that is equal to 100. And then we can go into array 0. And then you can see it gives me 100, right? And which one? This one?
Just like the star and penalty.
So it can mean a couple of things. In this context, it means that the type is a pointer to an int. So not the int itself, but a pointer to it, right? It's a place where an integer lives. This means look at this value, treat it like an address, and give me the value at that address. Does that make sense to you?
It's an address to an array then?
So this is, the array conceptually is literally just a block, right? The way we're representing that here is just the address of where the start of that array is. Okay. And so basically the idea is go to this point, right? And give me the value that lives at that point. Does that kind of make sense? Especially to, okay. So we have this, and then we can add as well, right? So we can go and we can say, right, +1. And then, so this is the equivalent of saying this. This is actually saying the exact same thing. So really, I should get 200. Array +1. So I should get 200 here because that's the same place. I can go and I can go array +2, and then that would give me array of 2, which should also give me 100, which you can see here, right? So you can go to this place and give me some offset from that point, and then dereference that. So is it clear what I'm saying when I say dereference? Kind of. So dereference means take whatever's in that parentheses, treat it like an address, and then give me the value at it. Okay? So this is how arrays work internally, and this is true in any language, right? Besides maybe like JavaScript and Python. But in C#, when you make an array, it is giving you a block of memory that you can index into it like this, right? Interestingly enough, in C, the bracket operator quite literally just turns into, internally, the compiler literally just makes that this. Right? So internally, this is exactly, like these two lines mean exactly the same thing. Okay? Which interestingly enough is why you're actually allowed to go this is valid. And I can go to array 1 and I can access it. Right? Why does this work? Because internally it's just addition, right? It literally just turns into 1 plus array is equal to 200. And addition, you can do whatever order you want, right? So one index of array is a totally valid thing to do. You should never do this unless you're a psychopath, but it is a thing that you're allowed to do. Okay. Are we kind of understanding the concept of arrays? Okay. So that's kind of the purpose of malloc is give me some amount of bytes, right? Is you request some amount of the bytes, malloc goes in, actually we can go in here, and there's a really big sequence of calls that are going to go into basically giving you that memory. And what it returns is the address. So you request memory, you don't know what address you're going to get back. The malloc decides where your memory is going to go. You get back an address and you get to use that address. Okay? Notice there's no guardrails here, right? If you're working in C# and you access array of 1 bajillion, like what does it do? Yeah, it's going to say, hey, the length of the array uh, is 100. You're not allowed to do that. What happens if I go, give me array of like 101, which really 100 is already out of bounds. Let's say 100, right? What do you think it's going to do? Where are the bounds? The only thing malloc gives us is like, hey, I've allocated this region of memory for you. Here's the pointer to the start of it. So if you say, yeah, take that start and go 101 sort of spots to the right.
Wait, so you don't know if it has memory for or not?
You have no idea. The answer is we have absolutely no idea what's going to happen here. This will probably work. Like this will give you, it'll either give you 0 or it'll give you random garbage. So if I go in here and we can run it, you see it gave me random garbage. Why did this happen? Like kind of intuitively, why? Like malloc said, I give you 100 spots. You access all the way. You access past the spot it gave you, right? Not really. It's whatever happened to be in the heap at that point. It's just whatever happens to be in memory at that point. It just says, sure thing, you're the boss. I'll give you what's there, right? Of course. So we don't have bounds, right? This is literally just an address to some region in memory, and you decide how you want to use it, right? So if you want, let's see how much I can push this. I can probably push it to 200. Right? And this gives you other random garbage. This is whatever happened to be in memory at that point. Okay. Can you see why this might be a security issue? Let me give me a way that this might be a security issue. If we just sort of naively allow this.
Is it gonna like randomly access like private files or something?
Not necessarily files, but any other program data, right? So like, what's stopping me from like just yoinking some data from like the operating system, right? So I mean, let's try it. Let's 20,000. You see it exited. If I run with debug, here's the exception we were getting before. It says you can't do that. So basically, the operating system, when you request some amount of memory from it, it'll say, I have allocated this memory for you to use, right? If you don't play by the rules and you try and access stuff that's like outside of what the operating system has given you, it'll give you an access violation. Okay. Interestingly enough, this number has absolutely nothing to do. So this is the address, right? So it says you're trying to access the array. You're trying to access this address in memory, right? And it says the operating system has said you're not allowed to do that. So it throws an exception. The program crashes. This is what we might call a segmentation fault. Has anyone ever heard that term before? It's basically you've accessed memory that you shouldn't have accessed, that you weren't allowed to access, right? The term segmentation fault comes from way back in the day when we had sort of basically every program is given like a segment of memory, and if you read past that segment, okay, well you've made a segmentation vault. Nowadays we have a more modern system called like paging, which I won't get into now, but it's basically a lot more flexible, and you're not necessarily guaranteed to have things next to each other. So the operating system does a lot of heavy lifting for you there. But basically, 200 was allowed because the operating system was like, okay, you asked for 100, but really 200 is like that's still within the valid range of things you can access, right? Um, on the other hand, 20,000 is like that goes somewhere way off into memory where you definitely don't have access to. Okay, is this all kind of making sense so far? Okay. Um, Addresses on the stack also have variables on the stack also have an address. So if I want an address onto the stack, I can get that very quickly by, first of all, exiting here. And then to get the address of something, the way I do it is I go ampersand. Okay? So if I go, oh wait, no, that's the address of the array. My bad. If I want the address of n, and then I go in here, run this, it gives you some number. This is the location that n lives on the stack, right? So remember, this is still going into memory. It's just managed by the compiler, right? So I can go in here and I can get a reference to it, and that's basically where it lives, right? So if I want n itself, I can go in here and I can say, okay, go to where n lives, right? Go to where n lives, find it, and give me the value at it, right? So does everyone understand why this gives you n itself? Why this would give you 100? Okay. How are we doing so far? Too fast, too slow, just right? Good, good. Okay. So this will give you just 100, which you can see there. Okay. So it's like, cool, we've malloc some data, right? We have our array, we can decide how much space we want to use, and the C standard library, where I had to import standard lib to do this, will decide where your memory goes, okay? Cool, how do I get rid of this? Like, I just have it, right? Before we had the stack, and whenever you would reach a bracket, right, it would just go poof, right, magically, right? It would just pop off the stack. This is persistent, right? So if I have, I can make a function called make int array, and I can say, I can take an int length here, and I can say, return just the result of this malloc. And then I can go is make int array of size n. Right, so I can go in here and I can do something like this. Does everyone understand kind of what this is doing? Right, so you're asking the CR library, can I have some memory? And you're returning an address to that memory, right? And so this allocation still exists, right? You still have access to it, right? So I can allocate something and it'll persist until I manually free it. So I can go and I can use my array. I can say, oh, okay, for I, int I equals 0, I is less than n, I plus plus, and I can go and I can, very happily use my array is equal to I. And then I can go in here and I can get rid of this using the word free. Okay? So before, with the stack, all of this was handled for you. Things were pushed onto the stack automatically, things were popped off the stack automatically. Now, since we're having to determine this at runtime, where we have the length is something we don't know, we're calling malloc, it's persistent, you have to explicitly go and say, I'm done with this memory, I'm going to free it. Okay? Does that kind of make sense? Okay, so what happens if, let's say I go here, and I say, okay, well, if n is equal to 100, for some reason. I'm going to go in here and I'm going to make my array. And for some reason, I forget to free. Okay? So I run my code, and then this array is here. Okay? Do I have access? Can I say free array in here? Why can I not say this? Yeah, exactly. Because the pointer, all of my information about where the array lives, right, is stored in this int pointer variable, right? So remember, when we go out of scope, this is an important distinction. The array itself, so the actual data, is stored on the heap. But the address to it, this int pointer itself, is stored on the stack. Does that make sense? Which means when we come out here, we've lost access to this, to the address. We don't know where the array lives anymore. So when we go in free array, it's like, what array? I don't know what you're talking about. I don't know where this is. Okay. So is there any way for me to free this memory anymore? Like once I've passed this here, is there any way I can ever get rid of this array? Yeah, I mean, you would have to, you have to be like somewhere in here, right? But like if for some reason I go like, whoops, and I forget, right? And I somehow find myself out here. Is that array ever getting freed? Okay, so what's going to happen to it? It's just going to live there until the program ends, right? Congratulations, we've had our first memory leak, right? This is what happens when you have a memory leak. It's you malloc something, so you have some dynamically allocated memory. You don't free it, but you've lost access to it, right? So what happens if I do this a bunch? Yeah. So remember when we looked at Task Manager? This will get to a big fat 100, and your computer will crash eventually. It'll get really, really slow, first of all, because malloc has to look for memory. It has to look for space. And if it can't find space, it's like, I don't know where to look, and it's going to have to do a bunch of complex things. It might even, interestingly enough, your computer is allowed to, in basically emergency situations, use your actual disk, like your hard drive, as memory. It's allowed to basically pretend that your disk is memory. This is called like swap space. So it'll start doing all sorts of crazy things like that. It can't find memory. All of your other things are having to, they say, I don't have enough space to work with. Your computer gets really slow. It crashes and yeah. So if I was just to malloc all the way to infinity, that's what would happen. So this is why we don't like memory leaks, and this is why in languages like C we have dangers of memory leaks, because we have these we control how much data we ask for, and so we have to control how much we have to give that back, right? So is everyone kind of understanding kind of what we've done so far? Okay. So let's talk a little bit more about like malloc itself. Why is this such a complex operation, right? Let's say I have my heap, right? And I go and I malloc A, and you're like, okay, fine, I can just give you that spot, right? And then I go and maybe A is of length like of length 2, right? And I go and I say, okay, I'll give you, you want like some allocation B, okay, I'll give you that of length 2. And then, okay, well, you want C, and then maybe you have one big allocation of length like 8 or something, and maybe that's D, right? So that's pretty straightforward. It's like, okay, fine, I have space for you, right? But then let's say the user goes, and actually maybe to illustrate this, I want to split this up a little bit more. So let's say these are all allocations of length 2, C, D, E, F, right? So far he's like, okay, well, wonderful, I have a space right next to this, I'll just keep giving you more memory. So malloc is looking very simple so far, right? What happens if I go and I call free on B? Right? Then that means it's like, oh, okay, fine. this space is no longer allocated. So I'm going to go and this space is no longer allocated, so this is free. And then, do I not have a, did they paywall erasers? No, they didn't, thank God. Okay. So it's like, okay, fine, we free this. And then you go and maybe you decide, oh, you want to free E, right? But now Malik basically needs to know, right? If I want to go and Malik and I request another 2 bytes, right? If I say I want another 2 bytes, it has to know that this is free and it has to know that this is free. So it has to know where these locations are. So it basically has to keep a giant list of where the free blocks are for it to do allocations, right? Okay. Let's say I want to allocate 4 bytes. And this is my entire heap. Can I allocate 4 bytes? Where would it go? Yeah, but like you have 2 here, you have 2 here. You can't split this up. This has to be together. Yeah. Uh, so Malik is going to go ahead and say, I don't have space, right? So this is a problem that's common in all sort of heap implementations, is that we have the possibility of fragmentation. Which is where I have 4 bytes available, right? I have this and I also have this, right? But they're not together, right? So we say that the heap is fragmented, right? Because we have enough free space, but it's all in different places, so we can't really use it, right? So the implementation of malloc will do all sorts of things to try and prevent fragmentation, to try and sort of merge free blocks together whenever it can. It has to keep a ton of state of, like when you ask for 8 bytes, let's say you ask for 8 bytes, it's actually going to give you quite a bit more than 8 bytes because it'll have some data that it has to store internally about that block that you just allocated, right? So it's to store a bunch of, we call this heap metadata, right? So this is extra information about, okay, what's the next block that's free? What's the, like, how big am I? Like when I call free, I need to know like how big is this actual block that was allocated. So there's a lot of extra metadata that gets stored, right? So the point I'm trying to make here is that malloc is actually a very, very complex function to call. Okay? But we need it, right? We need to do dynamic allocations at least sometimes, right? So that's what malloc does. So compared to the stack, right? Right. This is automatic. It's fast because it can be done ahead of time. We know exactly where we need and how we need it. All of the memory is managed sort of for us. On the other hand, malloc uses a heap, which is big, unstructured, but it's dynamic. We can kind of change things at runtime. Yep. So now do y'all feel like you understand the difference between like the stack and the heap? Okay. Let me see if there's anything I kind of want to talk about. Okay, so we talked about allocation. We've talked about memory leaks. Okay, so I'm assuming that y'all have never like actually seen like the malloc function before, right? But I do know that you'll have definitely seen new before in C#, right? What new does is internally it calls malloc, right? So whenever you say in C#, like my object O is equal to new object right? What this new keyword is doing is, among the lot of different layers of complexity, at the end of the day, it's calling malloc on something, and the language itself will manage all of this for you, right? So okay, when we use C#, right? So we've seen kind of how it works under the hood. When we use C#, we don't necessarily care about any of this, right? Like you make your variable, it exists, and then you kind of just use it, right? You never have to explicitly free anything, right? Um, why is C# able to do this, right? Like suppose we want to automate this, right? Where we can just kind of malloc things at will, but we don't necessarily manage when they're freed, right? Have you all ever heard of garbage collection before? The term garbage collection. Okay, so garbage collection is basically at some point we decided, hey, it kind of really sucks to have to always manually free everything, right? Because the example we looked at is like a really trivially like fixable memory leak. Like obviously just don't forget to free it. But some memory leaks get really, really nasty to fix. Because you can imagine as the complexity of your code increases, you have memory that's being owned and shared in a lot of different places. And managing all of that yourself is error prone. Actually, do any of y'all play Team Fortress 2? Kind of. The source code of Team Fortress 2 got leaked at some point back in like 2020 or something. And there's like lots of comments in the TF2 source code that literally say like, they go like, / this code causes a memory leak. Too bad. Like we're not going to bother to fix this. There are a very surprising amount of just like we don't care enough to fix this. Whatever, we're going to leak memory. Too bad. That's fine. So these get like really really nasty to sort of fix, right? So these like it would be really nice if we could automate this process, right? So we have different forms of garbage collection. Garbage collection is basically going to look into your heap, and it's going to look and it's going to see, oh look, I have an object here. It's not being referenced by anything else. I'm going to go ahead and free it myself. So it's a piece of code that's going to run in the background basically. It's going to run in the background, and it's going to free stuff for you. So languages like C#, languages like Java, right? They don't tell you where the addresses of your memory is. You literally just get a reference to the object, and you trust that the runtime of the language will handle that for you. And you also don't have to worry about manually freeing that, because there's a process that's sort of running in the background called the garbage collector, which is looking through all of the references you have in your code, and it's saying, oh, this object that is living in memory is no longer referenced by anything. I'm going to go ahead and get rid of it, right? So this is another layer of complexity when it comes to dynamic allocation. First of all, internally, even though you don't see it, whenever you call new in C#, it has to go and find a place in the heap for that, right? So it has to go and actually look for a place to do that. Second of all, it has to actually go and sort of manage those allocations for you. It has to go and check and see like, have we is this variable like safe for me to just go ahead and free? Does that kind of make sense? We won't get into the details of how actual garbage collection works, but there's two sort of main types of garbage collection if you're interested. There's what we call reference counting, and then what we call tracing. Tracing is probably the most common implementation of that is like a mark and sweep. Right, algorithm where it's going to go and sort of automatically do this. This is why a lot of languages like C++ or C are considered quote unquote faster than sort of languages like Java and C#. It's because languages like C# have to do with all of this runtime overhead of actually going and doing all of this for you, right? So whereas in what we call unsafe languages, in languages where you manage your own memory, we are in control of all of that. So there's no like extra garbage collection process that has to run. In other languages like C#, there's a process that has to run. Okay. Do you all feel like you'll kind of understand the concept of dynamic allocation a little bit more? Okay. We have about half an hour left, so in the second part we'll go into sort of more Unity specifics. Um, so keep all of this in mind when it comes to um, keep all of this in mind when it comes to dynamic allocation. We'll visit this when we actually talk about why do we care about why do we spend an hour and a half like talking about C when we just want to like code in Unity, right? Um, I want to talk very briefly about what CPU caches are. This will also become very important when we talk about dynamic memory allocation. Um, if you so far we've talked about, all right, you have your CPU, which your CPU is like kind of like the brain of your computer. It's the thing that's actually executing all of the instructions, running all of the code, right? And then memory goes and it lives off somewhere here. And then your CPU is going to go, oh, I want memory at this address, right? So it has to go and talk to memory, right? Um, so if you there's a few more layers to this that are quite important to know. So for example, if you like suppose hypothetically that you wanted like I don't know you wanted to like go and get a cookie from the store, right? So you go to a grocery store and you buy one cookie, right? And then you bring it back with you and you eat it, right? Or and the next time you want that a cookie, you go to Target or something and you buy an individual cookie, right? And then you come back, you go to Target and you buy an individual cookie and then you come back, right? That would get really inefficient really fast, right? Like why are you going to Target every time you want a single cookie, right? In practice, what would you do? You buy a box of cookies, right? You buy a box of cookies and then you keep them like at home, right? To avoid having to go all the way back um, to the grocery store, basically. Memory is basically like the grocery store here. You might have noticed if you open Task Manager, and then I go to Performance, you might see there. If I go to CPU, there are these things called caches, right? Where I have my L1 cache, I have my L2 cache, I have my L3 cache. These are the boxes of cookies, basically. This is the CPU saying, I'm not going to go to memory every single time I want a piece of data, right? I'm going to go every time I grab something from memory, I'm going to bring it back a bunch of memory with me, and I'm going to store it in a cache that's close, and it's quite small, right? So this computer has 32 gigs of RAM, right? But you can see that the L1 cache is only 2.1 megabytes. The L2 cache is only 32 megabytes. The L3 cache is 33 megabytes, right? So the idea of a cache is whenever I go to memory, I don't want to go to memory every time I want that same piece of data, right? I'm going to bring back a bunch of data with me, right? You're going to bring back what's called a cache line, which is usually like if I want a byte, I'm going to bring back a whole cache line with me. So I'm going to bring back usually 64 bytes is the size of a cache line. So it's like you only ask for one byte. The CPU says, okay, I'll bring back 64 bytes, and I'll take those surrounding 64 bytes and I'll keep them in my L1 cache. Okay. So this is you deciding that you're not just going to go and bring back one cookie every time. You're actually going to say, okay, fine, I only need one cookie right now, but I'm going to go and actually bring back a whole box of cookies. That way next time I don't have to go all the way to the grocery store. Does that kind of make sense? So your L1 caches are much faster, right? Like you can imagine, it's much faster to go to my pantry, open, and grab a box than it is to go and have to drive all the way to Target, right, or wherever, right? And so this brings us to probably one of those like interesting performance dilemmas that we have when we're programming, and this will come up a ton in game development as well. That sort of CPUs, right? This part of the equation has gotten really, really fast, right? CPUs can execute tons and tons and tons of instructions, right? The speed of your CPU is usually not the limit of like what you can do. So your CPU is really fast. You might have heard that like computers like they double in performance every however many years or whatever people say, right? So CPUs have continuously been getting really, really fast. However, the speed of accessing memory has comparatively progressed much slower. So accessing memory is still really, really slow compared to sort of all of the advancements that we've had in just how fast CPUs are. The implication of this is, well, what good is a really fast CPU if accessing data is really slow, right? So optimizing the caches, right? Optimizing the sort of the L1. In practice we have 3 levels, but we don't particularly care about the levels for our purposes. For now, we just need to know that we have caches and we can bring memory to it, right? Optimizing code such that it's friendly to the cache is a very big priority when it comes to performance. To kind of quantify this, so CPUs operate on cycles, right? So every there's a clock inside of your CPU, and every time the clock ticks, it does something, right? Something like a multiplication. So like, I don't know, x times y, right? Might take a handful of cycles, like 3 to 5 on a lot of like modern processors. This takes like 3 to 5 cycles. If you try to access memory, and what you do first, you look in the box of cookies, right? So you look in the cache. If it's not in the cache, if it's in the cache, so if you have if you have the data already with you in the cache, it's basically instant. However, if you have what we call a cache miss, so if we don't have the data we're looking for in one of these caches, and we end up having to go into main memory, this is hundreds of cycles. So I think a cache miss, it depends, but if you have to go all the way back to main memory, this could take like 600 cycles, potentially, right? So it's really, really slow, right? If we have to go all the way back to main memory. So avoiding cache misses, right, which is where the data is not in the cache, is a really sort of important priority and something that's worth thinking about. I want to show y'all. Does the concept of a cache make sense to y'all? Or do y'all want me to explain more? What's kind of not so clear? Okay, let's look at an example here. Maybe that'll go in here. You find one website. Bring this up here. It was this one, yeah. So this is some C# code, right? And you can see what it's doing is it's making a really big array, right? So it's making an array of whatever this turns out to be, and this is really big, right? And then so we're going to go, and we're going to have 2 loops, okay? Both of them are going to loop from 0 to the length of the array, right? From 0 to the length of the array. One is going to do I++, right? So every element. The other is going to sort of go every 16th element, okay? Remember how big is an integer by default? How many bytes? 32 bits, so 4 bytes, okay? So 16 times 4 is 64, right? So we're accessing basically every 64th byte, right? So the interesting thing about this example is that loop 1 is doing essentially 16 times the work of loop 2. Does that make sense why? Because it's having to do 16 times the iterations, right? This is doing every 16th element, this is doing every element, right? So this loop is doing a whole ton of work, right? Compared to this loop, right? But remember, when I go into an array and I access it, and I'm saying I want this address in memory, bring me this data back. we're not just bringing back array of I. We're bringing back array of I and a whole bunch of other stuff with us, usually about 64 bytes more, right? So really, we're getting this integer, but we're really also getting about 16 other integers in our cache basically for free. So when you actually look at the runtime of these, when you actually look at the runtime of these, you can see up until the 16th, right? Up until like k equals 16, right? So accessing every element, accessing every 2 elements, accessing every 4, every 8, every 16. All of these take virtually the same amount of time. So even though the loop that's going through every element of the array, so the loop that's doing literally 16 times the work of this array, of this one, is running in basically the same amount of time, right? And then afterwards, you can see now that you get into 32, right? There's a big drop off in runtime, because here's where you actually get to the point where you're actually where you're not having all of those integers in memory, right? So this is kind of cool, right? Like we can have a loop that does 16 times more work than another loop, but also runs in the same amount of time. And that's happening because of the cache. It's because whenever we access an element in an array, whenever we go to an address in memory, we're not just going to the address. We're going to the address and we're bringing back a bunch of stuff with us. We're bringing back a whole cache line. Does that kind of make a little bit more sense? Yeah. So that makes sense why we really like the cache, right? So this sort of thing, turns out, I think we've covered basically all we need to know about memory. Now we can start getting to sort of Unity-specific discussions. Whenever these sorts of things that we've talked about here really do form like the backbone of how we sort of try to be efficient with all of our state in programming, and especially game development, when we can have tons and tons of objects that are all sort of moving and doing their own thing and stuff. All of these sort of common optimizations that you will see in game development are very often having to do something with memory. Usually there's two things. Either you're optimizing for what we call locality, so keeping data close so that it gets pulled into the same cache, right? So we want to either write cache-friendly code, or there'll be some kind of optimization that deals with reducing the amount of dynamic memory allocations, right? Because we've seen that dynamic memory allocations are quite slow, right? So let's talk about, so all of this information is, even though you don't necessarily have to worry about it when you use Unity, it's the reasoning behind these things that we actually do some of the optimizations that we do. So let's talk about Unity for a second. When you call instantiate, you'll know what instantiate does in Unity, right? This is doing, internally, dynamic memory allocation. Dynamic memory allocation. The whole process that we talked about of having to basically, internally this will eventually call malloc, it'll go for a bunch of layers of complexity, but internally this will eventually call malloc, of having to find a place in the heap for this, of having to now, the C# runtime has to now go and actually manage all of this memory, right? So instantiate is doing dynamic memory allocation, right? It's just some layers removed from what we just did in C, right? But at the end of the day, it's not that different from what we did, right? It's not that you're basically just calling malloc whenever you call instantiate, right? So you can think of it in that way. So let's say I have a game and I have a little character, and let's say it's like a top-down shooter, right? And then so let's say my character has a machine gun, and then I'm going to, whenever I want to, I have a method shoot, I'm going to go and I'm going to say instantiate bullet. right? So every time I want to spawn in a bullet, I'm calling instantiate, right? And then let's say whenever the bullet hits a wall, we call destroy on it, right? So why might this be slow? Yeah, exactly. So every single time we want to spawn in a bullet, which if you have like a machine gun in a top-down shooter, that could be a lot, right? That could be once every few frames, um, and then every time a bullet hits a wall, you destroy it, and then next time you want a bullet, you have to instantiate a whole other one, right? So if you do this repeatedly, for simple games, you might not notice the problem. For larger games, this will absolutely like kill your frame rate. Um, Especially if you do it a lot. Any sort of like enemy spawning, especially for projectiles, um, especially if you were to implement like a particle system doing something like this, right? Um, any sort of repeated calls to instantiate and destroy are slow because of everything that we've spent the last hour and a half talking about, because there's so much complexity that goes into dynamic allocation, so much complexity that goes into garbage collection, so much complexity that goes into freeing memory once you've allocated it, right? So um, all of this complexity has to happen every time you want to instantiate a new bullet, right? Um, have any of y'all heard of object pools before? This is a familiar term. This is basically one of probably one of the best optimizations you can do just for any game. It is basically the bread and butter of avoiding having to do this. Um, Once you start thinking about object pools you'll see them everywhere and you can use them basically everywhere. This is I would say this is probably like the most important optimization in all of game development. What an object pool says is we're not going to bother calling instantiate every single time we want a bullet. What we're going to say is we're going to say, okay, realistically, are there ever going to be more than 1,000 bullets on the screen? Probably not, right? So we're going to say, okay, at the start of the game, when the game is being loaded in, instantiate 100 bullets. So go ahead and just give me all of that memory at once, right? Um, and then so now so we'll have basically a giant array of bullets. So we'll have a bullet array is equal to, here's one bullet, here's two bullets. You'll have however many bullets you want. Okay? This is all predetermined. You will say my game will have 1,000 bullets, right? And this you decide to instantiate the bullets. And when a game is loading, right? Nobody cares if there's a lag spike on when the game is loading. That's kind of when you expect things to be slow, right? So now when I want a bullet, do I have to call instantiate on it? No, why? Because it's already there. So what I can do is basically I can set these bullets to either be active or not active. Right? And in Unity, that's literally, you set a variable. You literally just, like, dot enabled equals false or whatever it is, right? So instead of destroying, right, instead of throwing out all of that memory that I'm going to reuse eventually, I'm just going to disable it. I'm just going to set it to false. And the next time I want a bullet, I'm going to search my array, and I'm going to find the next available bullet, the next bullet that's been destroyed, and I'm just going to enable it and then set its position, right? So we've gone from having to do all of the complexity of creating memory space, destroying that object, and then having to free it, right? And having to just repeatedly many times a second, to we're just going to do that all up front, and we're going to recycle. So whenever a bullet hits a wall, we're not going to destroy it, we're just going to disable it. And then next time we want a bullet, we're just going to re-enable it and then set its position, reset some variables, and then just use it again. So now that you understand kind of how dynamic memory allocation works, can you see why an object pool is so much faster? It's because we get to recycle all of the things that we did. So this is the intuition for why doing something like an object pool, pre-allocating everything, and then just enabling and disabling on the fly, it's the difference between having to do all of this super massive overhead and then literally just changing a variable, right? So that's the difference in complexity. It is amazing the kinds of speed ups you can get just by doing this. Um, this applies. Projectiles are kind of one example of this. This applies to anything. Any time you feel tempted to allocate memory and then destroy it repeatedly in a loop, you can probably use an object pool and you'll probably benefit from it. For example, you can have an object pool. For example, when like let's say the player gets hurt in a game, or the player like lands, like you jump and then you land and then there's some like dust particles. Come. Instead of instantiating a particle effect every time the player touches the ground, have a pool of particle effects that are all just sitting there disabled, right? And next time you want a particle effect, you just find one and enable one, right? If you do this for all of your different things, like anytime you constantiate, this is probably the single most important like if there's one thing you got from the last 2 hours, object pools are good, and this is why. Um, so hopefully it doesn't seem like magic anymore. Like there's a very concrete reason why we prefer to do an object pool versus instantiate and destroy, right? So you can use this for things like particle effects. Particle effects. You can use this for audio sources. Pre-allocate a bunch of audio sources, and instead of every game object having to manage its own audio, it just goes to the pool of audio sources and picks one, and enables one and uses it. Particle effects for enemies, right? When you have like a giant, like if you have like a horde shooter, like Vampire Survivors, right, where you have tons and tons of enemies, right? You don't want to be calling instantiate every single time you want a new enemy. You just want to go find one in the pool and enable them, right? So yeah, this is why we care about all of that. And it's because those sorts of changes in memory are so much faster, right? We have a couple minutes. I want to do at some point. Who's heard of Unity dots? Is a familiar term? This is the what Unity calls their data-oriented technology stack. Data-oriented tech stack. This is Unity basically saying we want to compete in terms of performance with other game engines. And remember when we talked about cache lines, right? And writing code that's friendly to the cache, right? Why was the cache? Why was caching possible, right? Remember how did we decide when to bring something over? Like whenever we access something, what else do we bring? We bring surrounding memory, right? So whenever I say like array I, I'm not really getting array I, I'm bringing back array I plus about 64 bytes or so of data that just come from the surroundings, right? So if this is your memory layout, right? If this is your memory layout, and you have one object here, you have another object here, you have another object here, and it's all just kind of scattered, right? Is this good for the cache or bad for the cache? To have things scattered. It's bad, yeah. Because when you bring something back, then you're going to have to go to another place in memory, then you're going to have to go to another place in memory, then you're going to have to go... You're going to be basically running around different parts of memory. It's you're going to... You're not getting as much use out of your cache as you could be. On the other hand, one of the bonus points of an object pool is that all of this is, remember, we're making an array, right? Of, let's say, like our array of bullets, right? Remember what we talked about, what an array actually is. It is a contiguous block of memory. It is literally a thing you go and you call malloc, and you go and you call malloc, and it gives you back a block of memory. That is internally what an array is, right? That has the added benefit of all of your data is literally just super close together, right? So it's all together. So contiguous memory, what we call what we call contiguous memory, is super, super great for the cache. Because every time you access something, you're getting something right next to it, which is very likely something you're about to access, right? Um, so this is why, right, we prefer our memory to look like this versus this. So this is a whole extra layer of optimization that's become super important recently in games, where we're trying to basically be mindful of our memory layout. So we like things like pre-allocated arrays. We like things like sort of loops that just go through one contiguous block of memory and do one thing, right? So I think eventually at some point, maybe next semester, we'll have a workshop on Unity dots, which is something that Unity has been trying to push recently. It's actually quite old. They've been talking about dots for at least the last like half decade, but it's gotten a lot more mature recently. And so part of what dots includes is something called, has anyone heard of this before? An entity component system. Component system. Does this ring a bell at all?
Yeah, I've heard of that.
You've heard of them? Yeah. This is part of what Unity calls their data-oriented technology stack. Any component systems are basically the entire goal of an entity component system is to optimize your memory layout such that you get like a ton of cache hits. Like this is the motivation behind doing an entity component system, is that we can take all of our data that would normally be very sort of scattered and then smush it together in a way that's super, super performant for handling lots and lots of entities, right? So we don't have time to get into this now, but the goal, this is like the motivation behind what Unity has been pushing for the last like 5 years is we want our memory to look like this versus this, right? And in certain cases, this will get you huge scales, particularly when you have a lot of entities, right? For things like a particle system where you have like a ton of particles, right? You really want to be optimizing your memory layout for that. So this is why we care about memory. It's because, for example, have you ever looked at like Terraria, for example, and you're like, how do they render that many blocks? How do they keep track of that many blocks on the screen at one point? At any point, how do they keep track of this entire like world? How do they keep track of so many different enemies? How can I just spawn in a bunch of stuff? How can I spawn in so many different particle systems and visual effects? Thanks, C2 Wi-Fi. Okay. Oh, okay, sure. Why not? Oh, we're back. All of that has to do with sort of understanding how memory works, why we like memory laid out the way it is. And yeah, so this is why basically understanding this and how this works is so like fundamental to anything that we do in game development, even though you're not directly dealing with something like C. But yeah, hopefully that was useful to y'all. Hopefully you'll understand memory a little bit more. And yeah, if y'all have any questions, I'll hang around for the next few minutes. But we went the full 2 hours for this one. But yeah, any questions, feel free to message me on Discord or talk to me right now. But yeah, thank you all for coming.